Balancing chemical equations, phi-psi family, let's get to it. We have to balance an equation because of something called the conservation of mass or matter. We'll tackle that at the end, but let's figure out how we actually can balance these beautiful chemical equations and learn a little bit more about them. A chemical reaction, as you know, is converting something into something brand new. So it could be a couple things, 2, 3 things, one thing, but something completely new is formed from that. And because of that, you have new physical properties and new chemical properties. If you recall back when we talked about physical chemical properties, think of a ripening banana. It goes through a chemical change because that bacteria is breaking down the banana. But it also changes not only because of the chemical reaction going on, and the decomposition, but also the color changes. It goes from yellow or green to brown or black. So those are all physical changes as well. Take rust on a car. No longer is that iron on the frame of the car, but that's iron mixed with oxygen to make rust, something completely different. And then burning gasoline. We know that isn't gasoline anymore once it burns. It has new physical and chemical properties, mostly in the form of gases or vapors because it gets so hot, exothermic. Now, there's 2 parts to every reaction. The left side of the reaction is called the reactants. That's everything that enters into the reaction. And then the right side is what you get at the end, the new stuff that's formed, which are called the products. Think of a multiplication problem. Multiplication problem answers, whatever you get at the end is really called the product. So that's an easy way to remember it perhaps. But either way, know your left side and your right side are called reactants and products. Now, the reason a chemical reaction occurs is because, like everything in chemistry, everything is trying to get more stable and lower energy. So when reactions occur, the substances that are formed are actually more stable. And often that has to do with the valence electrons. They're trying to get their outermost shell completely full. And a lot of times we say that's the octet rule, where we're thinking about 8 things. If we get 8 valence electrons, for some reason, atoms tend to be more stable, like the noble gases, and therefore don't want to react with much. So, lower energy, more stable, everything's good. That's why reactions occur. Now, if we look at a chemical reaction, or an equation of a reaction, we know there's a lot of different things. The chemical symbols we already know. Those are just the elements involved. Some are by themselves and some are in compounds. We also know and have seen that there's this arrow involved. The arrow either means yields or forms. So in this case, it's solid iron reacts with oxygen gas to form, that's what the arrow means, to form iron 3 oxide, okay, which is rust. But either way, know what that arrow means, to yield or to form. You'll also notice that there's things in parentheses, okay? The S, G, and S, okay, those stand for the physical phases of each individual substance. So S stands for in the solid phase, L is liquid, G is gas, and then AQ, something you might not be familiar with, is aqueous, which really means that it's something that was dissolved in water. So usually that's an ionic compound that breaks down into its positive cations and negative anions, and they're kind of swimming around in the water. But that is called an aqueous solution. Don't forget, too, these little subscripts, these numbers, as we've defined earlier, tell you how many of each element. 3 oxygen, 2 iron, 2 oxygen, no subscript here, so just 1 iron. We don't ever put the 1 subscript in there. Now, to balance a chemical equation, you're going to use these big numbers we call coefficients. They multiply anything in front of them for the compound or element that they're touching. All right, so if you started off, this was just 1 iron, 2 oxygen, 2 iron, and 3 oxygen. In order to get both sides of the equation, that means the reactant side and the product side, to have the same number of each atom, that means we have to use the coefficients to get those balanced out. And in this equation, we put a 2 in front of the iron 3 oxide because it would end up trying to equal out the oxygens on both sides. Here, 2 times 2 is 4 iron, which we have here, and 2 times 3 oxygen give you a total of 6 oxygen. 3 times 2 oxygen here give you 6 oxygen, and 4 times 1 iron gives you 4 iron. 4 iron, reactants and products, check. 6 oxygen, reactants and products, check. It is then balanced. So you want to get used to bouncing back and forth, balancing out on both sides. Bounce, bounce, bounce. So if we want to practice it, we look at this. There's 1 carbon, 2 oxygen, 1 carbon, and 2 oxygen. That's actually already balanced. So sometimes you don't even need to add anything to balance these guys out. If we look at the equation just a little bit lower now, originally the oxygens were not balanced. So we had to put a 2 here to make it 2 oxygen to balance out with these oxygens. So that's 2 oxygen, and now 2 times 1 is 2 oxygen. But because of that coefficient, it now made 2 times 2 hydrogen, which is 4 hydrogen. So because of that, it affected the hydrogen over here, and we had to do 2 times 2 hydrogen to make 4 hydrogen. So 4 hydrogen on the reactant side, 4 hydrogen on the product side. 2 oxygen on the left side and 2 oxygen on the right side. So everything's balanced. Now the question is, why do we even balance equations? What does it really matter as long as we know the ultimate original recipe? Well, recipe is a good word to use because you need a specific amount of each ingredient in order for the reaction to occur. Just like if you were making a cake, you need a certain amount of eggs, water, oil to add to your cake mix. So think of that. It has to do with the conservation of matter. The idea is whatever matter we start with, so in this case 4 hydrogens and 2 oxygens, even though it reacts to the product side, you still need to end up with 2 oxygens and account for 4 hydrogens. It just doesn't disappear. Matter just doesn't go somewhere and never return. It is still in our universe. So matter's never created nor destroyed. All the matter we have on this planet is already here. We can't get rid of it. We might not be able to see it anymore, but we can't get rid of it. So we have to balance equations in order to show that matter and mass is conserved. So another way to say that is whatever matter we start with, we have to end with. I often use this scenario for a field trip. We go on the field trip in the morning and say we've got 25 students and they're all sitting in seats. When we come back from the field trip, I don't care what seats they're in, but I have to have all 25 students or I might lose my job. So there's still 25 students, they're just rearranged and with new people. That's what happens with equations for chemical reactions. The stuff just gets rearranged, but it's never truly lost or goes away. So we have to account for that. Today we talked about balancing equations and also why we have to balance equations. Matter and mass must be conserved. Thanks for listening.